Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the velocity distribution in turbulent flow in pipes. So in our previous video lectures, already have discussed regarding the shear stress in the turbulent flow, and we have discussed about the Boussinesq equations and Reynolds expressions. Along with that, we have also discussed about the Prandtl mixing theory. So now we discuss about the velocity distribution in the turbulent flow in pipes. So in the previous videos, what we have discussed in case of turbulent flow especially, the total shear stress at any point, how we have calculated the total shear stress, we have calculated by considering the shear stress with the effect of viscosity and the shear stress with the effect of turbulence. So these two things we have considered to identify the total shear stress. Okay, now again in this condition also we have some points are there. What is that? The viscous shear stress, see that shear stress due to the viscosity or viscous shear stress, what we are calling, that is negligible at the boundary conditions. If you see at this boundary condition, this viscosity effect is negligible. So at this point we have seen, okay, in the boundary conditions, so that this turbulence viscosity or that the shear stress due to the viscosity is negligible. Only the shear stress due to the turbulence will be considered. So what equation we got previously, so that equation only can be considered, like tau equal to, we can consider this is tau turbulence. Okay, now we have seen the in the previous lectures, you have seen that lecture, that video. So there we have got that tau equal to, or that is actually in that time tau bar was there. Okay, so tau bar equal to, we have got this value rho L square, and here it is du by dy square. So this is the equation which was derived in the previous lectures from the Prandtl mixing theory concept. Okay, this is the turbulent viscosity or turbulent shear stress. Okay, now from this equation what we can see, now the velocity distribution, okay, that which is obtained, that is with relations of L, this mixing length. Okay, now see, this is the tau is there, so on behalf of this viscosity term is there, it is with a relations of this L, the mixing length is there. Okay, so how we can identify, let me draw the diagram actually what we have discussed in the previous condition. Suppose this is the x direction and this is the y direction, and we have a fluid flow in this direction, suppose. So here let assume that this is the flow is there. Let me draw this. This is the flow, and these are the one layer in the fluid flow. Okay, so the distance between each layers, was taken L. Correct. All the lengths between this each layers are L, and the distance from this boundary level to here, that was taken as Y. In the last class I have told you. So if you take, this is the average one, so to identify the velocity at this condition, velocity distribution at this point, that will be Y plus L, Y minus L. If you take this other next level, that is Y plus L. So by that we can identify the velocity distribution for this flow. So this one already have discussed in the previous. Now why I have just raised these issues, because the mixing length L, it is a function of Y. If you see how the Y is varying from this surface, along with that the mixing length also is changing. That means this mixing length is with a directly proportional, we can say, to the Y. So from here we can write the L is the nothing but the mixing length, okay, is directly proportional to Y. So Y is what? Y is the distance from this surface. Now this was already discussed previously, but here we need to consider the pipe condition. Now pipe condition also similar points will be arise here. Suppose this is the center one is there. Now from here if you consider, that means also same thing. What is the height is there from here to here? How much height is there? Okay, so each layer we have a again length will be there L, So from this point to this one, so what is the height? Same concept, but here it is, suppose if you are taken for the plate 1 and here you need to consider the pipe. So in this both condition, at the surface of this viscosity will be 0, so that the shear stress at this point will be negligible, and the distance of this from here to here it is y, and the gap between two layers is L, mixing theory length let's consider. Now for this one we can write this is L is directly proportional to K, so you can write L equal to Ky. So this K actually, this is a constant one. The K is nothing but this is a constant value, and this constant actually known as the Kármán constant. This is known as Kármán constant, and the value of this K also was given, that is 0.4. So we can put the value of K value, later equations we can identify. Now the point is, the equation what we got previously, this equation, in this value just put the value of L in that equation, so that we will start the deriving that equation for this condition, actually for this velocity distribution in pipe, turbulent flow in pipes. So what is the value we got here? Now L equal to, if you see, Ky. So that value we can put it in this equation of turbulence, shear stress for the turbulence. So here what I'll do, I'll just write down this equation. Now see, tau bar, or we can write this is only tau, so there is no confusion in this. So here what we'll get, rho Ky is there, so that one we can write K square y square, and this is du by dy square. Okay, this is the equation actually. Now this equation again I can write in what way I can write, let keep this du by dy square one side, and this remaining term we can take it to other side. So here what I can write, du by dy whole square one side, again other side I can write tau by rho K square and y square. So this is another side. So these things again what I'll do, I'll take, see this one, this total whole square is there, I'll take this whole square to the other side, that means root over will be there this side. Again one more line we can write it here, du by dy equal to root over of this one, this square it came to this side, so we can write root over of here, that is tau by, this is tau by rho K square y square. Okay, now again what I'll do, I'll just keep it, I will take this constant term outside and I'll keep this term here inside. That means I'll take this K square y square, let it outside. If you go outside, what will be there? Only Ky is there, and here inside what will be there? Now tau divided by rho. So this one we can give an equation 1. Actually this one already derived previously, in the last lecture we have derived for the Prandtl mixing theory, and this is equation 2 we can give. Now if you have seen, for a height of this y, okay, for a height of y at which point we are considering, for a height of y, if the y is very small or very close to the pipe boundary, because this is the pipe and this is the boundary of the pipe, correct? You can draw from here this side, and you can draw from this side. Now when the y equal to very small and that is near to the boundary, the Prandtl number need to be assumed to what? Tau to be constant. We have seen that one. So, and that is be equal to tau naught. Okay, when what I told, when the y is very small, I'm talking just about the conditions. Okay, so when y is very small, so tau will be equal to, so tau naught. Okay, because it is very the shear stress will be constant, and that will be equal to approximately tau naught. And what it reflects or what it presents, this presents that the turbulent shear stress at the boundary condition, the turbulent shear stress at the boundary condition, okay, we can consider this tau equal to tau naught. So this equation what I'll do, I'll just put it in this value. So what we can write again, the same thing, just to write du by dy divided by 1 by Ky root over of tau naught divided by rho. And this one we can give equation, another equation, equation 3. Okay. Now what I'll do, this equation, see, this equation is important one. Now we need to identify, we just need to do some exercise on the dimensions for this. Okay, this is shear stress and this is the density part is there. Okay, now I'll just convert into in terms of dimensional analysis. So this is shear stress. Okay, so we know that shear stress equal to, let I write here. So shear stress tau equal to, I can write, this is force by area. Again, force, what I can write, a force equal to, I can write mass into acceleration divided by area. Again, mass into acceleration, what I can write, a mass into acceleration, what I can write, a velocity divided by time. And this is as usual, again a is the area is there. Again, next term, what I can write, velocity I can write distance by time again. So this one, mass into distance. So distance, what I'll do, I'll just give L. Okay, length, and this is distance by time. Again, time is there in that, so tt time square, and here it is area is there, that means this one area. So area, again we can write L square. Correct. Now these things, if you write or you can solve it, like, means what we'll get. So tau equal to, in terms of dimensions, what we'll get. Now this is the mass. In terms of mass, I can write capital M. Okay, this is small m actually. Now I'm writing this in terms of dimensions, that is m, and this L is there. L, this L will be cancelled, only one L will be there, so that one we can write here L inverse, and this is t square, t also in the denominator. So if you take it to the numerator, so that will be t to the power minus 2. So this is the dimension analysis for the tau case. Similarly, here two terms are there, one more density is there. So density equal to, we know that mass by volume. So here again, mass by volume, we can write mass is m and volume is LQ. Correct. Length. So this is LQ. So what we can write, m L to the power minus 3. Now if you combine these two things and you will get this value, so that is tau by A or tau by rho. So what is the value of here? Now m L minus 1 t to the power minus 2 divided by m L to the power minus 3. So this things is there. Now if you cancel, m will be cancelled, and L to the power 3 is there. So now it is L to the power 2 will be there, minus 2 is there. So what I'll do, I'll take this one to up, this one I'll take to down. So what I'll get now, L square by t square. This reverse part is the minus part is there. I'll take it to denominator. This one I'll take it to numerator. So this is the value what we got from here. Now just put this value in this equation. That's it. So we'll go to the next page. So here what I'll do, I'll just put this value in this equation. So du by dy, I can write 1 by ky, and this is the value of now L by t. Okay. So okay, let's write here. So the value of what we got, L by t, we got from this dimension analysis. This is the value we got from the dimensional analysis of what we got now, tau naught divided by density. Okay. Now this length by this time, the length by time is nothing but what we know. We know that this is velocity. This is velocity, and this dimension is giving for this denotation of velocity, and that is known as shear velocity actually. So this velocity is known as nothing but shear velocity. This is nothing but the shear velocity, and that is denoted by u star actually. The u star is sometimes is used to written like this, u star subscript star, or sometimes is used to written the superscript star. So this one, it can be written in this way also. Okay, u star or u star, like that also you can write it. Now what we'll do, on behalf of this value, root over of this dimension analysis what we got, okay, we'll put the value of this one, u star. Okay, on behalf of this total root over of tau naught by rho, we'll just put the value of u star. So what we'll get here, du by dy. So I'll write here, let du by dy, what I can write, 1 by ky, 1 by ky, and this is u star, suppose I can write. Okay, now for the turbulent condition, actually for the turbulent condition, u star will be constant. Okay, so let integrate this equation. Okay, let integrate this equation. This one we can give an equation. Previously what we got, equation 3. Now we can give this is a equation 4. So again we can write, for the turbulent flow, u star is constant. So to integrate this equation, what we'll do, after integrating we can get it here, but integration of this one, dy, take it to other side. So integration of du will get u, again 1 by ky is constant, let no, y will be there, so 1 by k we can take it out, and this is u star as well as, so dy by y will be there, so that will be written log, that can be written log e y plus c. And c is the constant of integration that we know, and this one we can give equation 5. Okay, here I can write just integrate, so that you can understand we are integrating the above equation, and after integrating we'll get this equation. Okay, now this equation actually shows that the turbulent flow, this is the integration shows the turbulent flow, and the velocity this velocity is varies with respect to logarithm of distance. Now see, this is the logarithm of distance, this is the velocity, we know that this is the velocity is there. Now this velocity, okay, varies directly with respect to the logarithmic of distance. Distance is what? This is the distance, as I told you, this is the distance. So u is nothing but the velocity which is flowing inside the pipe. So this velocity which is flowing inside the pipe, that is directly proportional or varies with respect to this y. Y is nothing but the height, and that to be proportional to the logarithmic y. Okay, so we can say that the turbulent flow in the logarithmic, now we can say the turbulent flow, what I can say, the velocity distribution in the turbulent flow, we can write one more time, velocity distribution in turbulent flow is logarithmic in nature. You can see here, correct, u is directly proportional to the logarithmic to this y. So the velocity distribution, okay, the velocity distribution, why I am talking, because we are getting this velocity distribution here, and that is nothing but the u, correct. So this is directly proportional to the logarithmic of y. The same thing I am writing here, the velocity distribution in the turbulent flow is logarithmic in nature. Okay, so now to find out, see, this is the equation is not complete. Now this constant of integration is there. So to find out the constant of integration, we need to take the help of boundary condition. So the boundary condition we need to consider, let's consider the boundary condition y equal to r. This r is nothing but the radius of pipe we need to consider actually. Okay, this one, the total is diameter, so radius, this much height, as I told, this r, y, let y equal to r, and u let consider, we know that the velocity will be maximum at this point. At this point your velocity will be maximum. Now see, here the velocity profile came, again if you draw from this side, again you will get the same thing like this, because near to the boundary level we know that velocity is negligible, so that the shear stress is negligible. Okay, so now we can consider u equal to u max and y equal to r. Just to put this value in this equation now, so what we'll get, u max equal to u star by k, we can write u star by k, this one u star by k, and this is log e r plus C. Now what I'll do, I'll just I'll keep this C one side and remaining term other side. Then what I can write, now C equal to U max minus U star by K log E R. Now what I'll do, I'll just put this value in this equation 5. Okay, so that now put the value of C in the previous equation. Then what we'll get here, now see, U equal to U star by K, and this is log E Y, this is there. Now again plus U max, this one U max minus U star divided by K log E R. So now see, these two things are common, correct? These two things are common, only here Y is there, here R is there. So these things we can take it to, let me write here. Okay, now what I can write, we'll start from this U. Okay, so now we can write U equal to U max, this one U max, and these two things, let take it common here, and we can write U star by K, U star by K, and this one we can write, now see, log, okay, this one you can write log E Y minus log E, this is R, correct? Now these things again we can write what, U max plus U star by K, this is log Y minus log R, that means log A minus log B, that we can write log E, this one we can write Y by R. Okay, this is the equation. Now what we'll do, we'll just change this equation in terms of some numerical values. K value I already told you previously, the constant, Corman constant, and the value of this is 0.4. So what I'll do, I'll just put the value of 0.4 here, and next is this log E Y to the power Y by R, let it keep it like that. So now we'll keep this is U equal to U max plus U star divided by 0.4 log E Y by R. So this is the equation. And now if you want to just change it, you don't want to keep it this to 0.4, you can just also convert it into, like, Y equal to U max plus 1 by 0.4, so that one you can write 2.5 U star, and we can write log E Y by R, bracket close, and this one we can give some equation. Previously what we given 5, now we can write this is equation 6. This is the end of the concept. Okay, now this equation actually is called Prandtl's universal velocity distribution equation for the turbulent flow. Okay, this is also called Prandtl universal velocity distribution for the turbulent flow. Okay, now this equation also we can write, also varies for different kind of surfaces. Either it is a rough surface or smooth surface, for that also it will be vary. So this one is nothing but we can write Prandtl universal velocity distribution for turbulent flow. Okay, this is all. Now if you want to change this equation, like means if you want to mention applicable for the smooth flow as well as the other flow, not possible. This is only applicable for the smooth flow. So similarly, rough flow also you can use, but this can be written in terms of, you know, that this is for smooth as well as rough flow. Now again, if you want to just change this equation, we can write in such a way. That means we take this value into the other side. So let's write in such a way: u max, and this u value we take it to other side. That means u max minus u equal to, so this side will be minus, will be there. So minus of 2.5 u star, and this is log e y by r. Now what I'll do, this r, I'll convert this one, this my negative, I'll convert it here like this: 2.5 u star log e r by y. Okay, now this u star, let it take it to the other side. That means u max minus u divided by u star equal to what we'll get, 2.5 log e r by y, capital R by 1. This is actually in this term. Now this log, if you want to convert again in the other way, like that means in value terms, okay, so that also can be written. So this log e also we can change it to, let's write, this is 2.5. This log e r by y we can write in terms of 2.3 log 10 r by y. In this way also I can write. Now finally what we can write here, let's write here u max minus u divided by u star. Just to multiply this 2.5 into 2.3, so it will be near about 25 into 23, 575. So 575 means 5.75. 5.75. This is log 10 r by y, bracket close. So here this is the final equation, and this one equation you can give it equation 7. Okay, now this equation actually is known as, or you can say this is the difference between the maximum velocity, the difference of maximum velocity and the local velocity, difference of maximum velocity and the local velocity at any point of u max, at any point. See this u max and u, what is that? U max minus u, this is the difference of maximum velocity and the local velocity, and which is known as velocity defect, which is known as velocity defect. This is another one term, velocity defect. So this is all about this derivations of velocity distribution in the turbulent flow for a turbulent flow in a pipe. Okay, so these things actually is started from this in our previous lecture equation, what we got for this shear stress equation for the turbulent flow. So we got this equation in the previously, first thing. Why we have taken this equation only for the turbulent flow? Because we know that the total shear stress is equal to viscous shear stress and turbulent shear stress. Okay, the viscous shear stress is very negligible at the surface of the boundary, we know that. So that's why, that means the viscosity value is very negligible here. That means due to the viscous effect, the velocity is very negligible at this point, and the velocity distribution is not there, and that's why here shear stress, the shear stress at this boundary level also negligible. So that's why we have neglected this one, and we have taken this tau equal to tau t in the sense shear stress with the effect of turbulence. So turbulent flow shear stress. Now here what I have taken again, now the next term is L is directly proportional to the y. So L is what? L is nothing but the Prandtl's mixing length theory concept, we got the L value. L is nothing but the distance between each layer, the distance between each layer. So these are the things we got fit from here. So in that all we can conclude that what we have taken, the value of K we have taken, and we have derived the equation like one by one from here, and finally we have just did some dimension analysis here. From here we got this one, and finally next step we went. What is the next step is here? Just you have taken what the value is here, what we have taken. So the same thing we just kept on the previous equation, okay, and U star, we have converted this one to U star, that is shear velocity, okay, and this is the new term what we have considered here, shear velocity. And from that, if you see, we got this equation, U equal to 1 by K U star log E by C, and just to identify this value of constant of integration C value, and we have taken these boundary conditions, and we have just went for the integration of the, after integration this boundary condition came, and from that we got this value of constant of integration. Then again we put the value in this equation 5, then finally we got this equation. From there again we have taken, just we have derived, finally we got this equation. This equation is enough to identify the Prandtl's, this is actually called as Prandtl's universal velocity distribution for the turbulent flow, and it is implemented for the both smooth and rough pipe also. Now again, if you want to extend this equation, and finally we can have to go for the velocity defect, this equation. Here what we got here, just we have taken this U max minus U, that means maximum velocity minus local velocity, we got in the terms of this one. So I hope you understand this concept and this derivation of this velocity distribution. If you are having any doubt and query regarding this, you can give a comment on the comment box. Thank you all.